Hello everyone, myself Ruchita, currently pursuing my BE at Sri Venkateswara College of Engineering, Bangalore at the Department of CSE Data Science. Today in this presentation, I am going to present a topic related to discrete mathematical structure, and the topic is the binomial theorem. The binomial theorem. Before going to a topic, let me give a small introduction to the binomial theorem. The binomial theorem, which provides a formula for expanding the expressions in the form of a plus b to the power of n. If it is a fundamental principle in algebra and the combinatorics, the theorem allows for the computation of coefficient in polynomial expansion efficiently. Historical background of the binomial theorem. The theorem was first published or established by the mathematician like Isaac Newton and Blaise Pascal. It is a development was a crucial for the advancement of combinatorial mathematics. Understanding this history enhances your appreciation for the applications today. Basic definition of binomial theorem, which states that a plus b to the power of n is equals to the binomial. Here the binomial n of k represents the binomial coefficient. This formula is valid for a non-negative integer. Binomial coefficient means it is calculated using this formula as presented in the screen. It accounts the number of ways to choose elements from the set of n elements. Understanding this coefficient is vital for applying the theorem coefficiently, which tells the number of ways you could choose the x items out of n. And n of c of n, which means the number of ways the x items it is out of n. uh, Expansion or example, let us consider the expansion of x plus y to the power of 2, which equals to x power 2 plus 2x y plus y to the power of 2. Similarly, x plus y to the power of 3, which expands to x to the power of 3 plus 3x to the power of 2y plus 3x y to the power of 2 plus 3 to the power of 3. This example illustrates how the theorem is applied in the practice. The general form of expansion. The general expansion of the binomial theorem is a plus b to the power of n, which comprise the n plus 1 terms. Each term involves a decreasing power of a and an increasing power of b. The coefficient correspond to the binomial coefficient from the Pascal triangle. Pascal triangle is a triangular array that represents the coefficient of binomial expansion. Each number in the sum of two directly above in the triangle. The geometric representation helps to visualize the coefficient of an expansion. Application of probability. The binomial theorem is a fundamental in probability theory, which is especially in the binomial distribution. It allows for the calculating the probabilities of different outcomes in the binomial experiments. Understanding this application is crucial for the statistical analysis. In special cases, the theorem has a special cases such as a plus 1 to the power of n and a plus b to the power of n. These cases simplifies the calculation and are often used for the combinatorial proof. Recognizing the special case can save the time in problem solving. Theorem proof. The binomial theorem can be proven using the mathematical induction. The base case starts with n is equals to 0, which shows the validity. The inductive steps involves assuming it holds for n and providing for the n plus 1. Negative and fractional exponents. The theorem can be extended to the negative and the fractional exponents using the series expansion for 1 plus x to the power of minus k, and the generalized formula applies. This expansion burdens and applicable of the theorem is calculus and analysis. Relationship to the Taylor series. The binomial theorem is closely related to the Taylor series expansion. It provides a specific case of Taylor series for the certain function. Understanding this relationship is the beneficial for the calculus for the students. Computational tools, various computational tools can assist in applying the binomial theorem. Software like Python, R, MATLAB, and automate expansion. Familiarity with these tools enhances the coefficient in handling the complex problem. Visual representation. Graphical representation of binomial expansion can aid for the understanding. Visualizing the term which helps in the grasping how the coefficient changes with n terms. Diagram also illustrate the symmetric inherent in the binomial coefficient. Common misconception. A common miscomputation is that the coefficients are simply power of n terms. Another is forgetting to include all terms in the expansion. Addressing the misconcepts can improve the understanding and accuracy. Through this, it can skip the objects when counting. Counting object can be twice. Number conservation, which spread object out makes the number bigger. Not recognizing that there are big in counting does not matter. Practice problem. Solving the practice problem can enhance the comprehension of binomial theorem. Consider the expanding 2x plus 3y to the power of 4 as a challenging exercise. The frequent practice of solidifies understanding and application skills. Advanced application which includes the computer or algorithms for the cryptography. The theorem also plays a role in financial mathematics such as option pricing. Exploring these areas reveals the theorem's versatility. Summary of key points. The binomial theorem is essential for the expanding polynomial efficiently. Understanding the binomial coefficient and their properties is crucial. The theorem's application can extend across the various branches of mathematics. Future learning path. Exploring the combinatory further can deepen the understanding of the theorem. Studying the calculus while they reveal the more application in the series expansion. Engaging with the probability theorem can also enhance the practice application. Conclusion. The binomial theorem is a powerful tool in the mathematics. Mastery of this theorem opens the doors to the advanced concept and the applications. Continuous practice and the exploration will lead to the greater mathematical proficiency.